All of us have probably seen this remarkable feature of bird swarming at some point or the other. Have you ever wondered how it is that these birds stay together like that? What is the physics behind this phenomenon? Well, let us have a look. We first consider the term active and active matter. What does it mean? Well, one of the main features of active matter is that the individuals or parts that make up the matter consume energy. This means that active matter systems are always out of equilibrium. Most active matter systems are biological in origin, and we can find several examples in nature. Some of these examples are crowd behavior, swimming of school of fish, traffic dynamics, and of course, my favorite, swarming of birds. Now, the question that arises is how can we model such swarms? Since I'm unfortunately all out of pretty videos to show, let's get into it. In order to start understanding flocking, let us first look at the Wichita model. The Wichita model was first proposed in 1995 and is a seminal model of flocking behavior. Wichita proposed the model by drawing inspiration from magnetism and alignment of magnetic spins. Thus, the self-propelled particles, or the birds in the Wichita model, as shown here, could be considered to be like flying magnets. Every bird in the swarm moves with a constant magnitude of velocity and wants to align the direction with the average direction of its neighbors within a certain radius. And it does so with some imperfection, which is the noise in the system. The two key ingredients in the model for flocking are self-propulsion and aligning interactions. Thus, the Wichita algorithm can be explained in a few simple steps. For a given bird, we first find all of its nearest neighbors. Then, we calculate the average angle or the direction of velocity. And then, we align the angle of velocity for the given bird while incorporating some noise. Thus, we get the velocity angle update rule as follows. This noise is drawn from a random uniform distribution. So, what kind of behavior does this model show? Note that the model has three free parameters: the constant magnitude velocity, the density of particles that determines indirectly how many interacting neighbors they have, and finally the strength of the noise. We find that varying the velocity doesn't make much of a difference. However, the other two parameters are extremely important. Let's see. Here, I present the results of my own simulations of the Wichita model. We first start from a randomly oriented disordered state and evolve the system with different conditions. First, at high density and high noise, we see that we get some sort of overall ordering, but it is highly disrupted due to the high amount of noise in the system. Secondly, at low density and low noise, we see small clusters of particles moving together in different directions. And finally, the most remarkable behavior is seen at high density, low noise, where the entire system moves coherently in a spontaneously chosen direction. Thus, we see a phase transition from disordered to a completely ordered state. Let us try to characterize the phase transition by defining an order parameter, here defined as the average velocity of all of the particles. For a totally randomly oriented state, we would have the order parameter to be equal to 0, whereas for a completely aligned state, we have the order parameter equal to 1, since in this case, all of the particles are pointing in the same direction. Here, the order parameter is shown varying as a function of noise, and we clearly see a transition from disorder to order above a certain critical noise value. Now, having gained some insight into the flocking transition, let us look at the activizing model now. First proposed in 2013, it's an alternative, simpler model to work with compared to the Wichita model. In this, particles are modeled as having Ising spins of +1 or -1 on a 2D lattice that they can diffuse on. It is therefore akin to a sort of dynamic Ising model. Now, the key differences of the Ising model compared to the Wichita model are that the Ising model is a microscopic model defined on a lattice, and it possesses a discrete symmetry compared to the continuous rotational symmetry in the Wichita model. Particles are free to diffuse in the plane, but are self-propelled in only one of two possible directions, either left or right. Now, we can have multiple particles sitting on the same site, and thus we define the local density and magnetization at a particular site depending on the number of particles which spin up or down as given here. Now, do you recall the two ingredients required for flocking? They were self-repulsion and aligning interactions. Let us see how these same two ingredients enter into the active Ising model. We have two corresponding processes that incorporate self-repulsion and aligning interactions. These are correspondingly bias diffusion for self-repulsion and spin flipping for aligning interactions. These constitute a continuous time Markov process and have rates depending upon their spins. Let us first consider spin flipping. The rate of spin flipping of a particle with spin S at site I is given as follows, depending on the local density and magnetization. Thus, consider a particle with spin S equal to +1 sitting on site I. It will flip the sign of its spin with the following rate, as shown here. Correspondingly, for a particle with spin -1, we have the rate for spin flipping as, and it flips its spin as follows. Now, let us consider bias diffusion. As mentioned earlier, particles undergo free diffusion on the lattice, but have a left-right bias depending on the sign of their spin. A particle with spin S hops to the right at a rate d into 1 plus s epsilon, and to the left with a rate d into 1 minus s epsilon. Thus, for a particle with spin s equal to +1, it hops to the right with rate d into 1 plus epsilon, and to the left as d into 1 minus epsilon. Correspondingly, for a particle with spin -1, it hops to the left with d into 1 plus epsilon, and to the right with a rate d into 1 minus epsilon. Thus, spin +1 particles are biased to the right, whereas spin -1 particles are biased to the left. There is thus a mean drift of particles with spin +or-1 to the right or left with an average velocity ±2d epsilon. This mean drift is what acts as a self-propulsion in the model and can be tuned via the parameter epsilon. Thus, we have pretty much set up and explained the activizing model and how it incorporates the ingredients of flocking behavior, which is what I intended to do in this video. What remains is to simulate the model and see the results. We obtain a lot of interesting results upon simulating the activising model, such as this phase diagram, where we obtain three distinct phases, namely a homogeneous disordered gas, a polar liquid, and a coexistence phase. The crux of these results is that the flocking transition is actually best considered as a liquid gas phase transition. Since I'm out of time, these details have not been included here, and I request you to please look at my term paper for more details. So, ending with the same video I started with, here are given the references that I followed. And thank you very much.